Hello, I'm Marc Hildenbrand. I'm a developer advocate from Red Hat, and I'm very pleased to be able to record this for you on demand for Serverless Days ANZ 2020. The title of my talk you can see there, but I might just move to this slide here. This is a title slide that's in keeping with the theme of my presentation. As I said, I am currently with Red Hat, but I spent my time before that in consulting. So previously I had about 7 years in digital consulting with a company called TigerSpike. TigerSpike is a digital consultancy specializing in mobile development and is also an advanced AWS services partner. It was here in 2015 at TigerSpike when I was first exposed to the notion of serverless computing by way of Lambda, and perhaps most of you have been. I assume you have been because you're downloading this video. Since I've come to Red Hat, however, I've been fascinated by how much open source software, such as Kubernetes, which is at the heart of this presentation, full disclosure, can approximate the services that I previously thought were only possible on public cloud providers like AWS. That's sort of how this talk was born and why I'm really excited to be able to give this talk. One bit of full disclosure, I am using for a lot of the demo, a product of Red Hat's called OpenShift. For much of what I'm doing, I'll try and make it clear when it's specific to OpenShift, of which very few of it is specific to OpenShift. OpenShift is an enterprise Kubernetes platform. So most of what I'm showing you, if it works on OpenShift, it'll work on any Kubernetes distribution that is CNCF certified. So to get started, just as McDonald's popularized the fast food hamburger, AWS has popularized serverless by making it an easy to consume product, and it calls that product Lambda. There have been many implementations and iterations since then. Lambda was first introduced in November 2014 as a way of running a function within AWS Cloud, within one of its instances. For many, including me, as I mentioned, this was people's first introduction to serverless. Sysadmins were early adopters, using it as a sort of ubiquitous cron job, allowing scripts to be run on the whole of the AWS infrastructure. In my role at TigerSpike, we loved Lambdas. Often you just pair a healthy serving of Lambdas with an API gateway, and we'd be able to quickly write middleware microservices, or I guess micro functions, that allowed our mobile apps to communicate with the legacy backend systems for cheap, except when we got the DynamoDB settings wrong or something like that. But anyway, you get the idea. But for all of Lambda's many benefits, there are maybe two problems that are relevant to this talk. One is it's unclear how the burgers are made, sort of like when you do get takeout software. Now, I understand that it's deliberately opaque. That is the point of how serverless Lambda was presented to all of us. But that opacity can lead to some issues, many of which have been addressed, but famous issues were things like cold starts or noisy neighbors. That was another problem. But most pertinent to our discussion today, Lambda came to define the pre-existing and more general concept of serverless writ large. And with this came many other muddy understandings of what serverless and whether such functionality was even able to be available anywhere but in AWS or in a public cloud. So let's take a brief break from the serverless drive-through and see if we can home cook some serverless functionality for ourselves. So in this talk, I hope to define the concept of serverless more succinctly and to show you what we can learn about Lambda, that popular representation of the serverless movement, by cooking up a serverless implementation ourselves using only the finest open source ingredients. Specifically, we'll define and clarify some of the serverless concepts, a little bit nerdy and a little tiniest bit pedantic, but the whole point is just to understand this concept that isn't very well understood so we can kind of map out the space of possibilities and different tools and software that allows serverless. Second, we'll take a look at the serverless kind of the inner working. So using open source software, we'll take a peek behind one way serverless is expressed and can be implemented in open source land, specifically Kubernetes. And finally, we'll demonstrate this kind of homemade serverless. I'll show you a couple demos, and we'll do a little taste test at the end just to kind of compare and contrast this kind of approach to serverless with Lambda. So to start our quest of understanding of serverless, this quest of understanding, let's start with my stock up art friend here, Frank. He is a product owner responsible for Red Hat's website circa 2003. And this image here is courtesy of the Internet Wayback Machine, so the Internet Archive. It's real fun, you should go there. In 2003, anyone like Frank who was looking to deploy software outside software like this one here, this is Red Hat's cool store, had to not only deal with the complexity of developing the software, but they also had to take into account parameters like what are the usage patterns of the software as time goes on? When will the spikes come? How fast or slow will the user base grow over time? And what's the optimum hardware that would strike the right balance between performance and efficiency for this software product? Add to this the bureaucratic process and procurement hurdles for buying hardware, and you can see why Frank's just a little bit on the edge. If only he didn't have to worry about all the complexities of the servers that will undergird his site. Well, it turns out that computer scientists have been dealing with this kind of complexity for decades and might just have a technique to help approach this problem from first principles. So we're going to go back a little farther, but don't worry, we're not going to go all the way back to the dawn of time. We'll stop right here. Surprisingly, the main concept that would help Frank and is germane to our discussion comes from Grace Hopper in the 50s. So pictured here, she was in the military laboring to program the mainframes of the day in an era where using complex, low-level assembly code instructions was pretty commonplace in the computer science world. Whilst Grace's world of mainframes was anything but serverless, let's see what she can contribute to Frank's problem and see if it aids us in our task of serverless understanding. So I'm going to show you a clip. This is courtesy of Crash Course Computer Science. Some of you may be familiar with it. It's just a tiny edited clip that is relevant, and you'll see why in just a second.
This problem did not escape Dr. Grace Hopper. As a US naval officer, she was one of the first programmers on the Harvard Mark I computer, which we talked about in episode 2. This was a colossal electromechanical beast completed in 1944 as part of the Allied war effort. Programs were stored and fed into the computer on punch paper tape. By the way, as you can see, they patched some bugs in this program by literally putting patches of paper over the holes on the punch tape. The Mark I's instruction set was so primitive, there weren't even jump instructions. To create code that repeated the same operation multiple times, you'd tape the two ends of the punch tape together, creating a physical loop. In other words, programming the Mark I was kind of a nightmare. After the war, Hopper continued to work at the forefront of computing. To unleash the potential of computers, she designed a high-level programming language called Arithmetic Language Version 0, or A0 for short. Assembly languages have direct one-to-one mapping to machine instructions, but a single line of a high-level programming language might result in dozens of instructions being executed by the CPU. To perform this complex translation, Hopper built the first compiler in 1952. This is a specialized program that transforms source code written in a programming language into a low-level language, like assembly or the binary machine code that the CPU can directly process. We're once again moving up another level of abstraction.
So what you can see from that, just as the compiler helped developers focus on higher level concepts without being overwhelmed by the millions of lines of machine code that they had, that their programs translated into, the concept of serverless allows us to create a new level of abstraction for Frank and his website team. When developing software, we would ideally like to live at this level of abstraction, where the world is serverless and our business-specific code just runs magically, hiding the underlying technical complexity, and indeed the process, the bureaucratic, the procurement kind of complexity that made it all possible. You could say it's like a compiler for deployable software products. And I don't mind quoting myself. Sometimes only once is the only time it's going to happen in this presentation. So just like a programming language that goes with a compiler, this level of abstraction comes with some rules or principles that allow us to abstract the complexity. So if we abide by the syntax of a language, we can ignore some of the complexity that the language hides from us. So for the serverless level of abstraction, the first and most essential aspect is the concept of this service abstraction. To abide by this principle, we can't refer to any underlying infrastructure at this level. So instead of referring to servers and networks and stuff like that, we would rather refer to the services that are being provided. So think RDS, for those of you AWS fans, versus a named database server. So in building out our serverless, in red, our serverless definition, we start by focusing on the services that are not the underlying infrastructure. This allows us to reason about the website, in Frank's case, at a higher level, without having to fold in all the complexity of the underlying infrastructure. And while the servers and the other infrastructure are clearly still there, they are abstracted away at this level, in the same way that Grace Hopper kind of abstracted away the machine code and assembly that that those programmers could focus at a higher level of abstraction, again, without being overwhelmed by the underlying complexity. The next part of the serverless convention is that it should be event-triggered or event-driven. By using event-driven architecture, and more on that in just a minute, we can support the first principle, service abstraction, as we no longer expose the notion of servers and ports, such as web servers listening on port 80, 443 to handle HTTP or HTTPS requests. Otherwise, poor Frank, we're pulled back into that world of complexity, thinking about servers and infrastructure. By being event-driven, instead of the notion of a server and a port, we rather raise the conversation. We elevate this conversation to a higher level, almost another level of abstraction, merely by having event producers and event consumers. So let's see what we mean by event-driven architecture in a little more detail. First, what do we even mean by an event? Let's look at this in contrast to messaging. Messaging, which tends to be more serverful, is a bit more imperative. We tell things, do this, then do something else. This tends to put logic either into the caller or couple that logic with the given task or the implementation we're after. Eventing is a bit more declarative. It merely states that something has occurred. The key here is that something subscribes or listens to these events. The originator of the event does not specify the targets. So this slide here represents an example of event-driven architecture. And I'll just kind of move myself out of the way for a sec. So here we have an application in black that is a producer that creates events. Then we have a number of would-be consumers who subscribe and listen to those events, and each process them at their rate and timing. What's important here is that there's no coupling between the application, the producer, and the downstream consumers, except possibly the format of the event. And there are no server specifics needing to be exposed at this level. Unlike messaging, the application can largely remain unaware of the underlying handlers and the underlying handlers' infrastructure. I'll just move myself back down to the corner here. There, where I'm unobtrusive. The last key principle of serverless in the blank that we hadn't yet filled in was that the business logic is meant to be stateless. So why is this necessary? Well, it's not a principle that's unique to serverless. For instance, this is relevant to the 12-factor app principles of development. Also, when developing on containers, these tend to be immutable to start, so maintaining state is discouraged. However, with regard to the notion of the serverless level of abstraction, adding this constraint allows the following and provides perhaps some of the most famous aspects of serverless, like it allows for easy and theoretically infinite, horizontal scaling of business logic, again abstracting away the underlying infrastructure. And similar to the previous, the inverse of the previous, it allows scaling to zero. So something that can be woken up when an event is triggered. A lot of times it's a 0 to infinity scaling that people latch onto when they're trying to figure out what does serverless really mean out there in the wild. So now our definition is finally complete. Be aware that there are many other serverless definitions out there, such as this one, which you see to the left, that state these principles in a slightly different way or stress different aspects of serverless, sometimes merging it with another slightly lesser known concept, one that will lead us back to Lambda, kind of. So that's right. Lambda isn't technically serverless. Well, not exactly. Neither is it a glorified CGI bin, for those of you old enough to remember this, though it does give us a clue as to Lambda's true nature, at least from a computer science perspective. You see, Lambda is serverless in the way that a square is a rectangle. Lambda is a kind of specialized serverless. So you might more clearly define Lambda as function as a service. Function as a service, or FAS, however you do two A's in a row, is sort of like what would happen if the concept of serverless and the concept of microservices had a baby. Broadly, it's just another level of abstraction that can be made to build upon the serverless level of abstraction that we just defined. Like serverless, function as a service has its own principles that mesh well with serverless but don't strictly require it. These are a concentrated focus, so a focus on a single stateless piece of code, the fact that they're triggered, so something must start the function from the outside, they don't just sit there and pull, and this is not necessarily obvious, but it tends to come up, is that with function as a service, it's nice to kind of have this notion of revision management. So I can have a version of a service and a backlog, like a back history of function as a service versions, sort of like the revision control systems that programmers are used to with Git. So revisions tend to be packaged up so that they can be rolled out or rolled back, depending on what the needs are of the current production state. Now, where the two of these things overlap, this is where I would argue our friends Lambda and Azure Functions and Cloud Functions, these all live in the overlap between serverless and function as a service. Perhaps you can have function as a service without serverless, and you can certainly have serverless without function as a service. In fact, Google's Cloud Run and AWS's Fargate are examples of this. Now, I promised some home cooking. At this point, we're ready to talk about a key ingredient of our open source serverless recipes, namely Knative, but we'll get back to that in just a sec. Now, we don't want to cook for ourselves. It's always more rewarding to cook for other people. So remember our stock art friend, Frank? Let's see how we might update his existing website in this modern era. Here's the cool store in 2020. It's come a long way since 2003. For the purposes of our discussion, let's assume Frank runs his website on Kubernetes, which is also open source, and more specifically, as I disclosed earlier, on OpenShift, which, by the way, is open source, just as Kubernetes is open source. So here's the architecture of CoolStore. Lots of wonderful microservices in there, and let's pretend Frank needs to extend our website by adding the ability to process payment on an order, the area you see circled here in the red dots. So one way we could have done this is to have a traditional microservice kind of polling the order topic. It's a Kafka queue. But this is a little bit wasteful from a computational density point of view. Given that we have an event, an order, and we're already using stateless containers, Kubernetes, let's bake our own serverless to spin something up to process the item in our queue, and then in our order queue, and then spin it down when we're done. That's that payment service that you see here. And let's do that without Lambda and try and bake it ourselves. So let me present to you this Lambda-less payment service from my technical kitchen to you. So we'll come back to this recipe trope again and again to kind of look at the different facets of what it takes to make serverless on a Kubernetes cluster. First off, we need a Kubernetes cluster. As I said, this can be on-premise, off-premise, any place Kubernetes can run. It can happen in AKS, EKS, GKE, pick your Kubernetes service of choice, or, like I said, on-premise. For those who are not familiar with Kubernetes, or in a nutshell, it's like an engine that helps you to run containerized workloads in production. What's a container? Well, it's a lightweight, immutable virtual machine, and so much more, but that gives you kind of the idea. Like I said, we'll be using OpenShift, and specifically this is OpenShift installed in AWS, just full disclosure, and that gives you a sense of sort of, hey, this can kind of be run wherever. So in keeping with our baked it ourselves theme, the first part of this demo will be using something called code-ready containers. This is a way of running OpenShift on your laptop. But most of you will want to use something called Minikube, which is just the ability to run a Kubernetes cluster on your laptop. It's a great place to try out some of these kind of serverless concepts, right? Without any worries of sticker shocks or bills or anything like that. So we'll start our demo here with a small example of Knative running on my laptop. What we're looking to do here is take an ordinary, like Quarkus, like a Spring Boot kind of application, take an ordinary service and invoke it to start that service, that payment. We're going to start the payment service when something enters the order queue. So we'll take a look at that right now, running on my laptop. So first thing I want to do is just give you a sense of how easily you can install something like Minikube on your laptop. This is code-ready containers, but the installation process for something like Minikube would be similar. It basically is a Kubernetes cluster running on a VM on your laptop. And you see here, it just kind of starts up. I'll wait for that for a sec. Takes a little while to start up a cluster, but once the cluster is started up, not very long, then you're able to interact with it. So it's going to be called CRC. It gives me a login on my local machine. And then you'll see here that I can go, CRC console gives me the ability to just, it's a convenience function that allows me to kind of open the console. Then I log in with the credentials that it gave me. And then this is the developer perspective of OpenShift. It shows me the services, and there we go. So that kind of gives you an idea of what's going on there. And this shows me that it's kind of a cluster. What I can do here is I can also install different operators. We're not going to go into that now. Operators is a concept that exists, Kubernetes and OpenShift. And it's the idea of just being able to install things on my cluster. So just switching back for a moment. So that's the basic idea. I can do this all on my laptop, or at least the first part of this. The rest of the website goes beyond what my laptop can handle. So that's your idea. That's the idea, a Kubernetes cluster. So the next thing we need to provide is this service abstraction layer for our payment service. And this is where Knative, that I mentioned just before, this is where this enters in. So first, let me show you how this is folded into our Kubernetes cluster, and then we'll explain Knative serving in a little more detail. So in this slide, by the way, if the slides are made available to you, there's a link to a demo that will allow us to install Knative via an operator, the operators that you saw just a second ago. Think of as an operator as something that provides sort of software as a service in a Kubernetes cluster, sort of like what RDS does in AWS. So it kind of installs the software and is sort of like an automated way of making sure that software is continually updated, depending on the state of the operator. This works even for a cluster running in your laptop. So anyway, you can see the links after the presentation if you want to know more. So Knative is a project that was started by Google. It's been contributed to by Red Hat and others to build serverless for Kubernetes. Knative is the upstream open source project of something called OpenShift Serverless, which runs on OpenShift. To understand Knative at a high level, there are two subprojects that we need to consider. These are Knative Serving and Knative Eventing. So remember our definition of serverless? It's no accident that Knative has two components that somewhat mirror that definition. We'll talk about this in a little bit more detail when we go back to the demo application. Just to talk about levels of abstraction one more time, lowest level of abstractions on the bottom, highest level of abstractions towards the top of the slide. Knative is something that hangs out more towards the top. It's a higher order of abstraction building on top of all these other aspects of Kubernetes. Again, so that developers don't have to deal with all that underlying complexity of Kubernetes. This is one of the reasons that Knative exists, because of serverless, abstracting it all away. Thank you, Grace Hopper, or indirect thank you. Let's focus first on what the serving component of Knative can give us. This is a component that gives us the ability to spin up a container that we talked about before serverlessly. So it abstracts away some of that infrastructure complexity, as we mentioned in the previous slide. And instead, the developer interacts with a higher order concept of a service, which you kind of see here on the right. All right, yep, there you go. You see it there. So this is distinct from Kubernetes service. It bundles these things together, this notion of route creation, so ingress to the service, configuration, and revision management, right? The revision management we talked about before. There's even a command line interface and a plugin to Visual Studio Code that makes it even easier for developers to interact with Knative services. So by adding the Knative open source software to our cluster, we've added the service abstraction that is necessary for any serverless application. And we've also added a function as a service concept of revision management. We just threw that in there for free. So Knative Serving is doing that for us. Besides providing us a higher level of abstraction, Knative Serving handles a number of different things under the hood, some of which can be inferred from this default configuration of the Knative Serving component. Some of the main jobs of Knative Serving includes invoking the proper revision of our service, or revisions, which we'll see before we're done, determining when to scale up our services, and determining optionally when to scale our services down to nothing. So scale to 0, there's a couple properties here that I've highlighted. We won't go deep into all these properties, but one of these is the scale to 0 related properties. So enable scale to 0, stable window, scale to 0, grace period. This is all functionality that goes into whether Kubernetes Knative can spin a container down to 0 pods. And the time period that the autoscaler is monitoring the request and metrics to figure out how long those need to be 0 or at a low enough level to scale it down. Because you could imagine a world where you're constantly thrashing, taking pods down and bringing them back up. So there's some complexity in there. The other is concurrency related. So how many threads, how many lines of execution do I expect to be going through a container at any given time? With things like Lambda, that's usually one thread. With things like Knative, you can customize that and say how many threads you want going through a given container. We'll see some of that later. Next in our recipe, we want to create a container that our Knative service can wrap. And ideally, this is a small container that starts up quickly, right? Because we might be scaling it up based on demand. So let's take a quick tour of that service. So I'm going to take a look at let's see what does this container kind of look like? So for the payment service, what you see here, we're going to drop right into a project. That's just this is a Quarkus app. Quarkus is sort of like MicroProfile or Spring Boot. Think of it like Spring Boot, but it's got some very modern libraries and it starts up very quickly, even with the ability to compile the native. It's a Java framework. So you can see here, there's a whole bunch of properties that say that I'm going to post to a payment queue, a Kafka queue. And with those properties, the basic idea is that when I get a cloud event, I'm scrolling through all this, when I get a cloud event, I'm going to post to payment. And that's what you see there. It initializes itself connecting to a payment queue whenever I get posted to with a cloud event. Now what I'm going to do here is I'm going to actually kind of prove, hey, this is my Quarkus payment service that's going to be wrapped in Knative. So let's call it Quarkus local because I'm going to be compiling it locally. So this is my running Maven to compile it. Quarkus can be compiled in that way. This is showing something called source to image, which is functionality that OpenShift has. Basically, I'm going to skip through this. This is creating an image and hosting it in my Kubernetes cluster, my OpenShift cluster. So that's all building. It gets uploaded. This is just proving that it was built there. You can see, again, this is just this is the developer functionality that OpenShift builds on top of Kubernetes. And then at the very end, we're just going to tag that container, right? So we made a container in Kubernetes. We're housing it inside of Kubernetes, inside of OpenShift. And that's what we're going to use in the next part of our demo. So we'll switch back to the slides for a second. A little more to tell you before we do that. So having a container is not necessarily a sufficient condition for stateless, but running a container on Kubernetes is certainly helpful. Stateless business logic is not a principle that's unique to serverless, as we talked about before with the 12-factor app. But it certainly aids our serverless implementation as it allows our service, once wrapped in Knative serving, once bundled in Knative serving, tracked with those revisions, it allows for that easy horizontal scaling and the ability to scale to 0. So that's kind of what's going on there. So now let's take a look at what it takes to invoke this service. And again, this is still running on my laptop. So if you look here, this is inside of Visual Studio Code. I'm using the command line Knative version. That's just saying what version of the Knative CLI that I'm using. And what we're going to do in this is we're going to just call our isolated payment. So this service, if I just stop this for a second, KN service is creating a payment, a revision in the OpenShift image registry. Again, this is hosted internally in OpenShift. And it's just going to that container that we tagged in the previous step of our recipe. So now Knative is setting up its Knative service, and it says, hey, the Knative service is ready to go on my apps-crc.testing, which is great. So what we do here, this is my homemade serverless project. This is my Knative revision with my payment container at the center of it. And then there are a couple pods around the outside which represent the payment queue that I'm going to be posting to here on my local cluster. So in the yellow, I'm going to just listen on the payment queue so you can see when the messages kind of come in. So I'll log into the cluster and then I'll get on top of the pod here. That is a consumer. So I'll be able to print all the messages that come into the payment queue. And then what I'm going to do in this command here is I'm just going to curl to the route that was exposed by Knative, this payment.homeMadeServerless, apps.crc. You see it maps the information I'm finding from my developer console there. And then when I hit it, the little blue ring is telling me that it spins up. And as it spins up, it'll eventually come to one pod. And when it does, you will notice up top that I now have an order for Jane Doe. Congratulations, Jane Doe. And it says Quarkus local, which is just proving that this is the thing that I compiled before. I wait long enough and it spins down to 0 as I had configured it, that if nothing happens for 6 seconds, then you can spin this container down to 0. So now that we have our payment service posting to this Kafka topic, this payments topic, I'd like the payment service to be triggered when an order is placed in a Kafka queue. And this is where the event-driven side of serverless comes in, and specifically for us, where the Knative eventing, the blue side of the Knative project, makes itself useful. Knative eventing is a system that provides, I'll do some jargon here, composable primitives that enable late binding event sources, so producers, and event syncs with the following goals. So the basic idea is I can have a source that's bound to a sink, and I don't need both of them to exist before I can set up that kind of binding, right? So some of the principles that you see here, some of the design goals, Knative eventing is meant to be loosely coupled. It's, again, late binding. It can wait until the sink or the source or both of them appear before it activates. And it's extensible. It's meant to allow different plugins so that events can be generated from just about anything. You can think of it a bit like AWS Bridge, but for Knative services. So it's trying to turn anything that can happen into an event that Knative can ingest. So let's see what happens what that means by way of this event-driven architecture that we were talking about before. So I might just move myself up here for a second. So the basic idea of event-driven architecture we went over. Let's see what happens when we map it to Knative eventing. So it's the same stuff, gets slightly different names, and we care less about what happens on the other side of the sink. We're completely concerned with going from source to sink. So I have a Knative event source that publishes, say, a log event, and the sink consumes it and sends it off to the phone. Who cares? So that first one is the one we're going to spend the most time on, and it's our source to sink model. So the application is an event source, the actual handler is a sink, the two don't know about each other, and I publish what's called a cloud event, which you see down here. Right? That's an open source CNCF standard. There are two other methods of event-driven that Knative will support, and I'll just move out of the way in a second. One is channels and subscriptions, which you see here. So that's just basically saying there's a channel and multiple people can subscribe, not just one particular sync. So people subscribe later on. And then the last one is called the broker and trigger, which is like channels and subscriptions, just allows for some amount of filtering and stuff like that. So we're only going to see, as you saw before, as I mentioned before, the source to sync model. So before Knative eventing, we could only trigger our Knative services by HTTP invocation. Once we install Knative eventing on our cluster, which we can also do via an operator, we get the support of a number of different sources out of the box, like the Kubernetes API itself, or cron can spin up our Knative services, or Kafka, which we'll see in depth, or Google Cloud Services, and others that allows you the ability, as I said, to write your own kind of Knative eventing. So that fills in two other aspects of our definition. So from function as a service, we have the triggered, things are triggered through Knative eventing, and we have the the event-driven aspect. So these two things in the middle are our Knative eventing kind of contributions to our recipe. So let's go a little bit deeper. So we're going to look specifically now at how Knative eventing helps us with our website. So we're going to move to the cloud in this instance, because I don't have a data center in my house, and we're actually going to run this website and take a look at how our payment service works. What you see on the left here, over on this side, this is our actual cluster, the definition of our Kafka Bootstrap cluster listening on orders, and this is the source to sync model. The sync is a payment service, and that's what we're going to be looking at. So this is the cool store, and that's what we're going to take a deeper look at right now. So if we take a look here, now we're on the internet now. This is all the supporting databases and stuff like that. I'm going to just focus in on this aspect of the cool store. So I can click here. That's the actual UI front end of my cool store of 2020. And I can, up here, just like we did before, I'm going to listen on the payments queue or the payments topic of Kafka. I'm going to buy something. So I busily buy something. I'm going to put in a credit card, all the normal things you would expect from an e-commerce site. And then I'm going to check out. And when I check out, I take a look at all the orders and I see, ooh, they're processing. And it's just kind of sitting there, right? This is where the payment service, stupid payment service, where are you? You need to process our orders. So quickly just showing here's all the different operators, these different like extensible pieces on Kubernetes that I have installed. And I have to configure Knative eventing, which I do here. I tell it where my cluster, my bootstrapping cluster is. Kafka cluster, so many clusters in Kubernetes land. So I'm going to take a look at that same source to sync that we saw in the slide before. So orders is my source and my sync is the payment service. And what I'm going to do here is it's just a custom resource in Kubernetes. So when I apply that, now it has a notion of orders, but you will notice that it hasn't spun anything up yet because I don't yet have a sync. This is the late binding aspect, right? What's happening here is I'm actually doing some scripting to move things from my laptop registry all the way to the OpenShift registry in the cloud using a product called Scopio. We're going to skip that for right now. So all that's happening here is that I'm just moving my payment container that we saw before up into the cloud, into the OpenShift cluster in the cloud. Once I have it there, and you notice this is the image registry inside. So payment service, look at the registry inside the OpenShift cluster and create a revision. And I'm also going to set a concurrency limit, only 2 threads of execution at once, 2 requests at once, I should say. And then I'm just going to label it so that it shows up with the rest of our services. And this little square box in OpenShift renders a Knative service like that. And it has a payment service in the middle of it, which is great. Next thing I'm going to do is you'll notice the binding is set up now because I have a sync. So that's demonstrating the late binding. We have our payment service spinning down. You'll notice that the order has been processed. When it spun up, that was because of the late binding. The late binding kind of started and invoked my service because there was something in the queue. So if I refresh this, I would expect my payment to be, now it says Quarkus local. But the other way this could be triggered is not just by binding the service, but by placing an order. So we're going to do that right now. So I can go back to the website, and I'm just going to skip through this. So you get the idea. I place an order, just like I did before. And you notice as soon as I placed an order, this spun up. And when it spun up, one pod, and then you see again, Quarkus local for the latest thing that I bought, which was at, this time it was for test user instead of Joe Bloggs. So you get the idea there. And if I wait, it'll spin down to 0 just like it did before because it's not seeing any traffic at the moment. So the next bit of our recipe is mostly seasoning it to taste. How do we need, what is it that we need to do to make this work for our website and for our needs? So once we've set up our service to spin up on request, some of the things we would need to consider is, well, how many requests do we want it to handle at once? It's much better than trying to figure out how many servers to buy, but there's still some tuning that we can do. How many instances of our service should be running at once? And how do we ensure we avoid or at least minimize delays in startup? We don't want cold starts because containers can take a little bit of time to start up, depending on, remember, what you put in there. You can put any container and spin it up like a serverless service. So I'm going to show you 3 different demos that kind of come out of how we configure those things that I showed you before, the scale to 0, the concurrency, but specifically we'll look at the concurrency aspects. So I'll just do that right now. So one thing I can do with Quarkus is I can compile it for native. And what I'm showing here is just sort of, here's the default concurrency. And I believe you can see as I scroll through the container concurrency, the target default is 2, which I should only expect 2 requests at once. So I can take my Quarkus service and I can see what happens when I send 100 concurrent requests to it. So from the terminal here, I'm using this thing called Hey, which is just trying to generate load all at once. So I'm going to send 100 requests. And when I do, which I did previously, you see it will climb to about 50, which is more or less what I'd expect because there were 100 requests that come in, and every 2 should go to a single container. So by the time the 51st came, 1 container should already be up for that one. And that's broadly what we see here. We had 100 requests, 50% of them show the evidence of that kind of slower startup because I had to spin up the container in the first place. The second thing I want to show you is a little bit off the topic of like tuning, but it's about revisions. So I'll just throw it in here and then we'll look at some of the tuning later on. So some of the revisions, I can say, I want to call this Quarkus native. And now I want to compile Quarkus to native code. It takes a little bit longer through the magic of time-lapse photography. We're skipping through some of that. But once it's compiled, I get it to the image registry in OpenShift, which is what you see here. This is, again, the source to image dance. And once it's in OpenShift, so I'll just skip through this, gets uploaded to OpenShift. So that's our new container. I tag it Quarkus native. Again, just like it was in something like a Docker Hub. And then I tell it, hey, find me the image registry inside of OpenShift called Quarkus native. That's tag Quarkus native and wrap that in a Knative service. Now you notice that didn't overwrite my previous one. It just made me a new revision and made that the revision that gets 100% of the traffic. So now when I send hey, when I do hey and I send 100 requests, it's revision 2 that gets spun up with 50 requests. And you'll notice in the yellow, as I'm listening on that queue, I'm getting a whole bunch of Quarkus native coming through. If I then purchase something new, I should see Quarkus native being spun up, so by way of the queue. And the queue is the thing that winds up calling the HTTP endpoint in that case. And we see here my test user who just bought something, Quarkus native. And that shows me the distribution of the call to hey, which is, by the way, a bit faster because Quarkus can spin up a lot faster when it's compiled into native code. So we can also roll back in this manner. So we can go back to the original payment 1 if we want, and that's what you're seeing there. So I set all the traffic to payment 1. And now when I run hey, I'd expect this to be slower because I'm going to be spinning up the bytecode based Quarkus. And when that runs, you notice it's about twice as slow, most of the requests, just because of the speed boost that I get by compiling it to native instead of going through the virtual machine. And you get the idea. Same thing here. I can purchase something, and when I purchase it, when it's processed, you'll see it come back as, and if I look at the payment service, you'll see it come back as Quarkus local. So proving that no traffic is going to payment number 2. Now the last thing is that let's pretend we want to do some sort of A/B testing, and we have the 2 versions, or we want to do some sort of small dark release. We can say, well, or canary release is what I mean to say. We can split our traffic 50-50, which you see here, original and native, and we can say payment 1, payment 2. And then when I send a hey request like I did before, we go back over here, we send 100 requests to the same endpoint, that same route, and Knative handles the splitting of traffic between the 2. So both of them will spin up to about 25, though the UI may not show that. And we expect to see a mix of the local and the native calls come through the queue. And now you see a mix, spikes at the 3-second and the 10-second kind of level, kind of representing how long the 2 revisions can take. So you may notice that we haven't really addressed the concentrated focus of function as a service. And that's right, because that depends on you. The heart of serverless, at least in the Knative world, is the container. And that's kind of the blessing of it. You can turn just about anything that's containerized into a serverless service. It doesn't care how it got there, old Knative, it just wants a container. If you want to put that container on Rails, in a way like how Lambda is a bit on Rails in terms of what comes in and what kind of things run and how it runs, you can make it feel that way, but that's something you kind of have to do yourself. And there are other products out there, OpenFast and stuff like this, that kind of works towards that goal. In some ways, we've demonstrated some function as a service by like showing how our containers can get built and uploaded into something like an OpenShift or your own image registries. But it's still a bit different, which brings us finally to our summary taste test. So first off, function as a service. Lambda is truly function as a service, whereas Knative is sort of a function as a service kit, like a salad kit. You need to build your own, though there are plenty of open source projects that provide a truly function as a service, whether it's based on Knative or otherwise. Open function as a service is an example of that. I don't believe it's based on Knative. Speaking of open source, open versus proprietary. While aspects of Lambda, the Lambda offering are open, such as Firecracker, the kind of lightweight VMs, the code that runs serverless in Kubernetes is fully open from top to bottom and can be run anywhere Kubernetes is run. In terms of orchestration and scheduling, Lambda workloads are not scheduled through Kubernetes, though there are some similar Kubernetes kind of concepts. But instead, Lambda runs on these highly tuned proprietary system that's optimized to deal with large numbers of workloads and anti-correlated workloads. And there are plenty of resources on the internet about how that all that stuff works. Whereas again, Knative reuses the Kubernetes scheduling kind of algorithms and horizontal pod autoscalers and others. We'll talk about that in a second. Containers. Whilst Lambda runs in a container, well, sort of, it's more on this virtualization layer, this Firecracker layer, to provide security between workloads. Knative is using containers, 100%. In terms of scaling, Lambda scales based on incoming invocations. Knative serving scales based on concurrent requests and load. But with the help of some other open source projects, one called Kata, coming from Microsoft and others, you can scale based on arbitrary metrics, such as the depth of a queue, like a Kafka queue. With OpenShift, there's also this other thing called a machine autoscaler, which allows a Kubernetes cluster to grow based on incoming load and requests. So your cluster could conceivably grow, which makes serverless even more kind of appealing in those worlds. In terms of concurrency, each Lambda invocation can only handle one event at a time. That's generally the rule. Knative allows an administrator to adjust the maximum number of concurrent requests in a service, as we demonstrated. So while both use event-driven architectures, the nature and format of the events are slightly different. So Knative uses this open cloud event format. Lambda's format is proprietary but tuned for use within AWS. And finally, AWS is able to provide a truly pay-for-what-you-use kind of service to the end customer. For Knative, the savings come from a more efficient use of the compute you have on your cluster. And I might just move myself out of the way. Though without scale, it might be tricky, right? Because you have overheads to run Knative on your cluster in the first place. When coupled with things like OpenShift, you may be able to get that pay for what you use in terms of this ability to scale and add more machines for burst kind of situations. But broadly, when you're talking about serverless in Kubernetes land, you're talking about making more efficient use of your memory or your compute dollar on the cluster. So where have we been? We've spent some time defining and clarifying what serverless is and using Grace Hopper as a patron saint of levels of abstraction, the kind of mother of the compiler, if you will. So serverless, we understand, is a separate concept from function as a service, but the two can be bound together to get something like AWS's Lambda. We looked at Knative as the Kubernetes native way of implementing serverless anywhere you can find a Kubernetes cluster, in the public cloud, private cloud, on your laptop. And finally, we looked at what it might look like to cook up Kubernetes kind of your own serverless recipes, if you will, as I say this kind of tongue-in-cheek. But the key was containers. In Kubernetes serverless land, it's containers that are running, and it's up to you to define those containers in such a way to make them look function as a service or whatnot. So kind of like home cooking, you can have it your way as it says there, but it will take just a little bit more effort. So I hope you enjoyed this message. That brings me to the end. Feel free to connect with me on LinkedIn should you be watching this on the internet someday. Hopefully I'm still at that address. And I thank you for your time. I hope you enjoyed this Serverless Days talk.